Friends, today we are going to discuss the chapter number 3rd from course CH 333 Organic Chemistry T.Y.B.Sc. So name of the chapter, the nucleophilic substitution reactions at aliphatic carbon. So here we remember what is meant by the nucleophile, what is meant by the substitution reaction at aliphatic carbon. So we remember what is meant by the nucleophile. Means we remember any negative charge species or the species with having the electron rich or electron rich species is called as a nucleophile. Suppose here you take an example of OH minus. OH minus having the pair of electron, it is electron rich. Like next example, that is Cn minus, it having also the electron rich species. Such type of the species we call nucleophile. So what happen? Again you take example of suppose RO minus. So all that are the example of nucleophile. So nucleophile is nothing but electron rich species. Then what is meant by the substitution reaction? The substitution itself indicate a reaction in which atoms or group of atoms which is replaced by atom or group of atoms of reagent is called substitution reaction. Means in case of substitution reaction, the nucleophile is replace the living group from the substrate, and instead of that living group there is a nucleophile is there. So that's why the substitution reaction is nothing but a reaction in which a group of atom or atoms is replaced from reactant or substrate by the reagent atoms or group of atoms. Such type of reactions is called as a substitution reaction. Here you take one simple example. When there is a methyl bromide and there is a OH minus. Suppose you take this example. This methyl bromide is called as reactant or it is called as substrate. What is your reagent? Here we use NaOH is a reagent. This is a substitution reaction. And what happened? This OH minus is called the nucleophile. And when we write a reaction or we write a product, after completion of the reaction there is a formation of methanol CH3OH, and there is a Br minus is leave out or it is depart from the substrate. So that's why this is the reactants, or sometimes we call the substrate. OH minus is nothing but a nucleophile. NaOH is your reagent. This is an example of substitution reaction, or we call hydrolysis of methyl bromide. In presence of alkali, there is formation of methanol. So methanol is a product, and this Br minus is called as leaving group. So this is a one simple substitution reaction. So this is a nucleophilic substitution reactions. So why we call the nucleophilic substitution reaction? Because we see this is your reagent, and reagent having the nucleophile OH minus electron rich species, and this species is replaced by Br. So that's why instead of Br, in case of products we write OH. Means your nucleophile from the reagent is replaced by Br, and that's why this reaction is called nucleophilic substitution reaction at aliphatic carbon. And in this case, we remember from the substrate which group is depart or which group is leave out from the substrate or reactant. There is Br, and so that's why Br minus we call as a leaving group. Leaving group is nothing but it leave out from the substrate or it depart from the reactant. So that's why Br minus we call as a leaving group. So when we think about a nucleophilic substitution, so there is a 3 or 4 terms is very important. Methyl bromide we call as reactants or substrate. OH minus is called as a nucleophile. NaOH is act as reagent. this methyl alcohol or CH3OH is called as a product, and group is leave out from the substrate or reactants is called as a leaving group. There are the various examples of the substitution reaction, and here we take Rx is your substrate or alkyl halide, then OH is your nucleophile. There is a formation of alcohol and we write X minus is your leaving group. When we change a nucleophile, you take a Rx or alkyl halide is your substrate, Cn minus is a nucleophile, then formation of RCN, and X minus is nothing but leaving group. So there are so many examples of a nucleophilic substitution reaction. Then we remember what happened in case of nucleophilic substitution reaction. And we take one general example. Suppose that is methyl bromide. They are hydrolyzed in presence of NaOH, formation of methanol, and Br minus is leave out. It is called the leaving group. So two things must happen here. What happened? When we think about the mechanism of the substitution reaction, we are thinking about a mechanism. So two things must happen here in a substitution reaction. So which is these two things? The first thing, the bond between carbon and bromine is break, or breaking of bond between this carbon and Br. So this bond is break. And what is the next? The carbon and OH bond formation. We take example of any substitution reaction. There is two things is happen here, and the first thing is that the bond between carbon and bromine or leaving group is break, or the breaking of bond between carbon and Br or leaving group. And what happened when we see the product? There is a formation of bond between the carbon and OH. So you take any nucleophilic substitution reaction, two things must happen here. The bond between carbon and leaving group is break, and bond between carbon and nucleophile is formed. The question is arise, what arise, when and how? Means what happened, when and how the bond between carbon and bromine are break. We see this, the bond between this carbon and leaving group is break, bond between carbon and nucleophile is formed. Then the questions are arise, when and how bond between carbon and Br is break. The second question is that when and how the bond between carbon and hydroxy group or carbon and OH forms. And the third important question is that, so what is the energy changes or occurs when the bond between carbon and leaving group is break, and when the bond between carbon and nucleophile is formed. So these three questions is very important. When and how the carbon bond between carbon and bromine is break, when and how the bond between carbon and OH or nucleophile is formed, and what is the energy changes occurs or associate in these nucleophilic substitution reaction. Then the depending on the sequence of which bond is formed first and which bond is break first, or what is the sequence of breaking and formation of bond between carbon and Br and bond between carbon and OH or nucleophile, the nucleophilic substitution reactions categorize into two parts or two types. The first one, the Sn2 reaction, and second one, Sn1 reaction. So these two category of nucleophilic substitution reactions are with two types. The first one, the Sn2, second one, the Sn1. So this type of the reaction is depends upon what is the sequence of bond formation and bond breaking between carbon and Br, and between how the bond break or form between the carbon and hydroxy group or nucleophile. So here we first discuss, or we will discuss the first reaction, and that is Sn2 reaction. And here we want to discuss the Sn2 reaction. Then you write for the example of Sn2 reaction. Simple example, hydrolysis of methyl bromide in presence of OH or NaOH. We call the hydrolysis, and in presence of NaOH. What happened? What is your product? Methanol is the product. There is a Br minus is a leaving group. We got here substrate, OH minus we got the nucleophile, methanol we got the product, and Br minus we got leaving group. So this is a simple example of Sn2 reaction. So we see the first part, that is the kinetics. Kinetics of Sn2 reaction. So what is the kinetics of the Sn2 reaction? Means we study the kinetics of the Sn2 reaction, then we observe that the rate of reaction is depends on the concentration of methyl bromide as well as the concentration of OH. So means what? The kinetics of this reaction, the rate of reaction is directly proportional to the concentration of methyl bromide as well as concentration of OH minus. Then we write the rate is equal to K2 and the concentration of methyl bromide and concentration of OH minus. Means what? The kinetics of the Sn2 reaction, the rate of reaction is directly proportional to the concentration of methyl bromide as well as the concentration of OH minus. Then we rewrite the equation, rate is equal to K2, that is K2 is the second order rate constant. Means in Sn2 reaction, rate of the reaction is depends on substrate as well as a reagent, or methyl bromide as well as a OH minus. So we change the concentration of methyl bromide, or we change a concentration of OH minus or nucleophile, then the rate of reaction is changed. So that's why the Sn2 reaction is a bimolecular reaction, or it is a second order kinetics. Means what? The rate of reaction is depends upon the two molecules. The first molecule is methyl bromide and second molecule is OH minus, is nothing but nucleophile. So that's why Sn2 reaction is a second order kinetics. Then what happen in reactions? When we think about organic reactions, then there is a one term, that is a rate determining step. Rate determining step means what happen? Suppose you take a reaction or a reactant, they are converted into the D, but they are not converted into D directly. So A is converted into B, B is converted into C, and then C is converted into D. Means what? So this conversion A to D having the three steps. This is the first step, this is we call the second step, and we call this is the third step. The rate of reaction depends on which is the slow step of the reaction. So there are so many steps in the chemical conversion or organic conversion. So 2 steps reaction, 3 steps or 4 steps, whatever may be. But overall rate of the reaction, this rate of the reaction depends on the slow step of the reaction. Means what happen? A is converted into D by 3 steps. A is converted into first B, B is converted into C, C is converted into D. And suppose we say the second step is a slow step. Then what happen? The overall rate of this reaction totally depends on how the B is converted into C. Means which is a slow step of the reaction, and such step or such steps of the reaction is called as rate determining step. Means overall rate of the conversion of A into D totally depends on the second step, because second step is a slow step and overall rate of the reaction depends on only the slow step. Rate of reaction not depends on how A is converted into B or how C is converted into D, but overall rate depends on how B is converted into the C, and this step means B is converted into C. This step is a slow step, and this step we call as a rate determining step. Then what happens when the bond is break or bond breaking? Means we remember in organic reactions the bond is break, or we call bond breaking. So we remember when we want to break a bond, then we want to supply the energy, and that's why bond breaking is an endothermic reaction. Endothermic reaction means we want to break a bond, then we want to supply the energy, and that's why bond breaking is an endothermic reaction. Means we want to supply the energy when we want to break a bond. When the bond formation and when in any chemical reactions or organic reactions the bond is formed, then energy is given out. Means bond formation is a exothermic reaction or exothermic process. So you remember well, when bond breaking takes place, then we want to supply the energy. This is an endothermic reaction. When bond formation takes place, we remember well, the bond formation is an exothermic reaction. Means when the bond between 2 atoms is formed, then energy is given out, and when the energy is given out, so that's why these reactions we call exothermic reaction. Then once you discuss this part, then we will discuss the mechanism of Sn2 reaction. So and when we want to discuss the mechanism, when in gold propose the mechanism of Sn2 reaction. And what is the mechanism of Sn2 reaction? We remember there is a substrate. We take an example of methyl bromide, and you take a nucleophile OH minus. OH minus is attacked from the back side of the CBr bond. Then there is formation of a transition state, and this step is a slow step, or we call RDS, rate determining step. This is your substrate methyl bromide. This is your nucleophile, we know. Then this is the rate determining step, or we call this is a slow step, and formation of transition state. And there is a formation of transition state. and after formation of the transition state, this transition state is easily converted into the product, or easily collapse or quickly collapse into the product. So what happened? The Ingold is proposed the mechanism of SN2 reaction. And what happened in SN2 reaction? Nucleophile is attacked from the back side of living group, and then there is a formation of a transition state. This is a slow step, or that is a rate determining step, and in case of this transition state, the hybridization of carbon is sp2. When we see the substrate, what is the hybridization of that carbon is sp3. And we remember, when the nucleophile is attacked from the back side to the substrate, this is a slow step or rate determining step. There is a formation of a transition state, and in transition state the carbon having the 5 groups, and we remember this transition state, the carbon having the sp2 hybridize. This transition state is a crowded transition state. The carbon having the sp2 hybridize. The bond between these two groups is 120 degree, and that's why the transition state is easily collapse or convert into the product. And we remember what happened in this case. We see the transition state. What happened in transition state? These 3 hydrogen and carbon, they are present in a single plane. And what happened? This hydroxy group and this living group, or suppose this is a 3 carbon, they are present in single plane. This is a hydroxy group, and here we write a living group. So that's why transition state is very crowded, and it easily converted into the product. So what happened in transition state? Why the backside attack of nucleophile takes place? The question is arise. This is a nucleophile. The probability is same. Either this nucleophile is attacked from the front side of the living group, or this nucleophile may be attacked from the back side. But Ingold describe the mechanism of this reaction, and in SN2 reaction, nucleophile is always attacked from the back side of living group. And why the nucleophile is attacked from the back side? Because we remember this is the substrate, and when the nucleophile, suppose we say the attack from the front side or from the side of the living group. So that's why we remember this living group having the negative charge, your nucleophile having the negative charge, then this transition state is more crowded, or this front side attack is more energetic. It requires more activation energy, and then the rate of reaction is a slow down. And again, what happened here? The Br having the negative charge, or this OH having the negative charge, so there is dipole-dipole repulsion is there, and to avoid that dipole-dipole repulsion, the attack of nucleophile in SN2 reaction is always takes place from the back side. So backside attack, what happened? These Br and nucleophile, they are apart from each other. There is no dipole-dipole repulsion is there, and the backside attack is less energetic. It required less activation energy, and so that's why in SN2 reaction, nucleophile is always attacked from the backside. Then once you discuss this, then we want to discuss the energy profile diagram. Energy profile diagram. For SN2 reaction. And in energy profile diagram, we plot a graph between potential energy changes. This is a potential energy changes with reaction coordinates. And then we see what happened here. So this is your reactant. What is your reactant? Methyl bromide plus OH minus. This is nucleophile. In this case, attack of nucleophile takes place, and there is a formation of a transition state. And we already know how to write transition state this way. This is the transition state, and then there is a formation of products or product. What is your product? This methyl alcohol and Br minus. Then how much energy is required to form the transition state? This is called delta E. Delta E is nothing activation energy. And when the product formation takes place, then delta H amount of energy is given out. There is a difference between energy between the products and the reactant. So this is the energy profile diagram of SN2 reactions. This is a reactant methyl bromide reacts with a nucleophile OH minus, then the attack of nucleophile, then there is a formation of a transition state. This transition state requires this delta E is a activation energy. Once the transition state is formed, because it having the high energy, and this transition state is easily converted or quickly converted into the product, and there is a formation of methanol. So this is a energy profile diagram for the SN2 reaction. Then we want to know what is the stereochemistry. Stereochemistry of SN2 reaction. So what is the stereochemistry of SN2 reaction? We take one simple example, means we already discussed this nucleophile is attacked from the back side to reactant or substrate. There is formation of a product, and when we write a product, it's a methanol. And when we see what is the position of leaving group and what is the position of a nucleophile in product. So in case of reactants or substrate, leaving group in a right hand side, and when we see the product, then nucleophile goes to the opposite side of a leaving group. So what happen means, what is the position of a leaving group, that opposite the nucleophile is attached in a product. So that's why when we see the stereochemistry of SN2 reaction, there is an inversion of configuration. So inversion means what? This leaving group is in the right side, leaving group is leave out from the right side, and when we see the product, nucleophile is attached from the opposite side of the leaving group. So ultimately there is an inversion of configuration. When we take a chiral carbon or substrate having the chiral center, and then we see the stereochemistry, suppose your reactant having the R configuration, then after SN2 reaction your product may be the S configuration. Means what happened in SN2 reaction, there is an inversion of configuration. Because why there is an inversion of configuration? Because attack of nucleophile takes place from the opposite side of the leaving group. So leaving group is depart from the one side, and nucleophile is attacked from the opposite side, or nucleophile is attached in opposite side of the leaving group. So that's why in SN2 reaction there is an inversion of configuration takes place. Means reactants having the R configuration, then product having the S configuration after SN2 reaction. When reactants having the R configuration, then product having the S configuration. After there is a SN2 mechanism is there. So that's why we remember in SN2 reaction there is a inversion of configuration is there.